here today, and a warm welcome to Anuradha Annaswamy, and thank you again for flying all the way to Lausanne today. So, Dr. Annaswamy is founder and director of the Active Adaptive Control Laboratory in the Department of Mechanical Engineering at MIT, and she was previously a member of the faculty at Yale, Boston University, and MIT. Her research interests are very broad, and they span adaptive control theory as well as its applications to automotive, aerospace, propulsion, as well as smart grids and smart cities. She has been the recipient of many awards, so that's why I needed to note them down, including the George Axel B. Outstanding Paper Award and the Control Systems Magazine Outstanding Paper Award. She's also a fellow of the IEEE and IFAC societies, and she has received the Distinguished Member and Distinguished Lecturer Award from the IEEE CSS, as well as the Presidential Young Investigator Award from the National Science Foundation in the US. Further, she has served as the president of the Control System Society recently in 2020. So today, Dr. Annaswamy is going to tell us about cyber-physical human systems and social responsibility. And we are very much looking forward to your talk, and the stage is yours.
Great. Thank you very much. Appreciate that very kind introduction, and thank you again for inviting me to come to Switzerland. I think this is my third or fourth trip to the country, and it's actually a lot of fun to come to a place where you can actually see the mountains around. So and we have nice sun out today, so it's a pleasure to be here. Thank you. So what I want to talk to you about is cyber-physical human systems and social responsibility. As Giancarlo mentioned in his introduction, we are beginning to move towards a point in control systems research where humans are not an afterthought, but humans are actually at the center of the whole conversation. So I want to, before I talk about social responsibility, I want to first frame the conversation with cyber-physical human systems. The second point I'd like to make before I actually go into the slides themselves is I don't have any track record in this particular topic. I, like you all, are very much aware that this needs to be the conversation, and I just want to raise more questions in today's talk and really have an extended conversation with you all as to how we can go about answering those questions. So most of what I'm going to do today is just basically frame the conversation, and let's start moving the dialogue in the direction where humans are at the center and not an afterthought. So cyber-physical systems, that particular phrase is something that was coined probably, I don't know, around 2010 or something like that. And US National Science Foundation started this initiative, and they basically came up with this kind of a flower diagram where all aspects of society, all aspects of engineered systems are seeing more and more of a concentrated cyber footprint, whether it's energy or chemical or automotive or medical or civil or materials or manufacturing. Across the system, there has been more and more of a digitization, processing of information and decision making, which really brings the conversation to a framework where you don't explicitly think, okay, here is a physical system and draw the boundary, and here is a computer controlled aspect of it, but really look at it as a whole so that you can understand holistically how is it that we should go about designing these systems. So obviously the cyber aspects have to do with computation, communication, and control. And on the physics side, you've got natural human-made aspects which obey physical laws. And then what happens is that these things, as they begin to interact, they're multidisciplinary, they're interactive, they have to be coordinated, they have multiple timescales, they're highly networked, and perhaps require new system science. And across the board, what you're seeing is that in all of these things, the role of humans, as again Giancarlo mentioned, is increasing. And not only is it increasing, there are different ways in which the interaction between humans and automation are beginning to manifest themselves. In some cases, like the example that you see in rehabilitation robotics, humans and machines actually have to work together as symbiotic autonomous systems. In many other cases, there are more supervisory operators that, and this kind of a role is not just that they provide some oversight, but they really have to understand exactly what the guidelines are that they have to provide to automation. And what really we are seeing again and again is that these humans are not just mere observers or outsiders, but they actually begin to participate in the overall system operation in a more concerted way. So humans in the loop is, again, a terminology that is very well understood and has been around for a long time. And this is becoming even more, taking even more of a center stage in the context of self-driving cars. Humans as multi-agents, again, I think become more and more prevalent as we understand how to intertwine automation in the service industry and provide interfaces that become more immediate and that are more action oriented. So in all of these cases, what you see is the variety of interactions. And if I can use this opportunity to do a little bit of advertisement, Controls for Societal Scale Challenges Roadmap 2030 is a document that we are putting together that will appear, we hope, by the end of this year. And in that, one of the sections talks about cyber-physical human systems, and that brings in actually the story of what are all the different ways in which humans and automation interact very nicely. For example, human in the plant. Sorry, that the title got switched. Human in the controller. And again, I'll, as we go through the talk, I'll give you more examples of how they all come about. Or again, human-machine symbiosis. So these are all different ways in which the interactions occur. Another way in which we can do the taxonomy is when it comes to scale. Human and multi-agent loops. So you could have a physiological interaction, which is probably what we look at in the context of medical devices and robotics. Or you can have both the human and controller participate in terms of automation and process. And again, I'll touch more upon this as we go into the details of an example. Or one where there is basically a network population and with a wide interaction, which again makes the domain of where the human role stops and where automation begins, and that boundary becomes a lot more blurred. So in all of these cases then, before we go towards social responsibility, let's just sort of try and understand what some of these examples are and to see to what extent we have started to understand the role of humans and how we are able to provide some system-wide performance goals and achieve them. So this phrase, cyber-physical human systems, therefore, is a very appropriate rubric to consider the overall interaction. And for instance, we started this IFAC series of workshops, a biennial one, and the next one actually is going to happen in 2022. If you've not made your reservation, please do so and come to Houston, which is just before the CDC. And this, again, provides one of the forum for really presenting the works that happen under this umbrella. Another one that is coming, again, a bit of advertisement here, is a book that is going to be released by IEEE Press, and I think it's going to appear early 2023. Also something that really talks about the conversation between how humans interact with cyber-physical systems. So this is basically what I would like to do in my talk today, to talk about 3 different examples. Okay, the first one is cyber-physical human systems in smart grids. And the example that I would like to go over is humans as empowered prosumers. And again, for those of you who are getting introduced to this term, the idea is that as consumers, we are just not merely consuming electricity, but by virtue of the rooftop solar that we may have on the top of our homes, we also have the opportunity to produce electricity and therefore a producer. And so the concept that I'd like to go over, what the concept is that we've utilized in here, what the performance is that we seek to achieve, and then talk about what exactly is the role of social responsibility here, which in this context is primarily energy justice. So the second example that I'd like to address, again, interestingly enough, all of these examples are application domains that are very much part of NCCR. So it's great to see the sectors that you're taking a look at, and they are indeed provide a fertile ground for investigating social responsibility. Highway traffic is a second. And again, the human participation here is humans in the loop. And the concept that we are going to investigate is the notion of transactive control. And the performance goal here is one of alleviating congestion. And again, what are some of the inequities that occur in this context? And what is, again, the role of socially responsible automation? I'd like to talk about that. And then I'd like to conclude with what happens in the context of flight control, where humans are in the form of pilots who are basically co-designing the overall decision-making together with autopilots. Okay, let's start with smart grids. Now, there's been a number of recent events, and I'm sure the story that I'm going to tell you here, there's a similar one in Europe as well. But the story that I'm going to see in the next few slides is more US-centric, but it is unbelievable as to the number of events that have happened just in the last year. For example, the beginning of 2021, there was a severe weather issue in Texas where they experienced incredibly cold climates. And there was a whole bunch of things that happened because there was an extreme cold wave followed with rain and ice and snow. And since the overall grid was completely ill-defined for that kind of extremes, there was a whole sequence of events that took place as a large-scale system, and it seriously affected the entire state. And I mean, that's a whole talk in itself, but let me suffice it to say that this was a significant event. Another one, and again, I'm sure the United States is not alone in this. There's a big effort in expanding and modernizing the electric grid. It started as a fairly large initiative, but fortunately there was a particular bill that the US Congress was able to pass, which is again looking at a significant effort in a deep carbonization of the grid. So for instance, what we would like to achieve is basically 100% clean electricity by 2035, and there's a lot of effort afoot in order to go towards that task. As you start to increase the cyber footprint in order to exchange information, another thing that is also happening is that there are adversarial behaviors that are coming into the picture, and that again is another interesting event that I think very much focuses our conversation on how exactly we need to have this interplay between humans and automation go forward and provide and be socially responsible. So interestingly enough, all of those things is really introducing new stakeholders into the picture. And interestingly enough, in all of those things, consumer is very much literally and figuratively in the center of the conversation. Because what really needs to come together is a coordination between bulk generation, transmission system, distribution systems, the entities that serve load, markets that basically affect these decisions, renewables, and how you are able to coordinate renewable generation with bulk, demand response, the notion by which as the supply becomes more intermittent, you have a way of adjusting the demand so that power balance is achieved, storage, so that when the sun doesn't shine or the wind doesn't blow, you have a way of making sure that the transition between one asset mix and another is smooth, and so storage. Power electronics that provides the right interface in order for the dialogue to occur. Microgrids, that's a microcosm of local generation and adjustable load and storage. And electric vehicles. So all of these things really will have to come together in order to realize a whole. And again, note, consumer is very much in the center of that conversation. So this is not a trivial problem, because what we're talking about is basically coordination of a huge system that has got an enormous number of individual decision making and and in a position of authority. So this one, for instance, is a figure of the Polish grid, and that at the transmission level has these kinds of numbers, and every little blue and red dot that you see are basically nodes that are capable of providing an input into the grid and affect the overall grid performance. And so imagine if many of those dots basically correspond to empowered consumers, then we have an exceedingly complex set of interaction between humans and automation. And indeed, that's the direction in which we are moving. So this is not science fiction, it's very much a fact. This is another example of a large scale system. Now, this is a distribution grid where what you see is basically a huge number of batteries in all houses, which with measurement capability, with rooftop solars, with some sort of centralized decision making, which is the substation, and another endpoint control in the form of inverters. And depending upon the kind of phase that you have, meters that measure things even in all of the three phases and so on. And so if you look at what really you have to do in here in terms of overall optimization, the kinds of numbers are mind-boggling again. So you can have a scenario where you have 200 primary feeders, 400 secondary feeders, 1,000 IoT devices, and 100 PVs per secondary feeder, 200 batteries. And if you do the numbers very easily, it becomes a billion endpoint control problem. And within this scale, you have to now imagine that you put consumers into the mix. And it is those consumers that we have to serve. In fact, that's indeed the objective of the grid, to provide an essential service, one of electricity, to every node that is in this grid. And how do we then engage in an interaction with those humans in a responsible way? And that is the challenge. So I want to quickly walk you through a specific example. And then, of course, in the midst of all of these things, and we were talking about this conversation earlier, I know there's lots of information in here. Just focus on the third bullet, if you will. So one of the things that you want to do is to make sure that privacy is preserved. Data that the operator gets, the grid operator gets, does not compromise your anonymity in any way. And so how do you make sure that the decision-making tools basically allow the appropriate use of all of these emerging tools that you have, like, for instance, coordinating IoT networks in the power grid? So one thing that we did was to say, okay, now that you've got this sort of multiple endpoints, here is a way in which you can look at the distributed optimization. And I just want to walk you, let me take 2 minutes through the exercise. We said, okay, here is an optimization problem. Here is how we can actually assign complexity by doing a certain partitioning. And that means that you have to introduce new dimensions, because you have to have copies which manage the coordinated constraints. Then we are able to take the whole problem and convert it into an atomized optimization problem. But we want to make sure that this optimization problem is solved, keeping privacy in mind. So that was our whole goal. And so here was some amount of regularization that we introduced into the picture. And we did a dual assent approach in order to do the optimization. And we also had to do this optimization taking into account the fact that there were extra copies, and that allowed us to atomize each of these things separately. And then this said that, yes, you can indeed go about doing solving and guaranteeing that this distributed optimization will have a solution under some conditions. And we then said, okay, let's go ahead and test it in the context of a real grid. And this is a simulation exercise. And what we wanted to do is to basically show that here is an algorithm where you can have, so imagine you have a whole bunch of distributed solar, and all of them are able to provide some injection. So the idea is that each one of them is basically compensated for the kind of injection that they're providing. And the local compensation from in that grid basically provides with a local distributed LMP, locational marginal price. So that's how they're getting the incentive for participating in the market. And so what we showed was that by providing the kind of distributed optimization framework, we are able to actually increase the revenue for a distributed system operator. So it goes to show that you can have this sort of prosumer type of idea and encourage them to participate in the market. So what this showed, when in the context of the simulation of the Japanese distribution grid, that when you provide a certain boundary condition, this is the distributed LMP, and you can show that that's what happens in that section of the segment, and the same kind of calculation does occur in a distributed optimization framework across the entire grid, and each of them is locally reflective of what is happening in that particular grid with the local amount of injection and power injection and consumption. So what this says is that, yes, indeed, you can accomplish a multi-tiered structure of a market structure, and that market structure at the end of the day has all of these different components, which mirrors the electrical co-location in terms of a high voltage grid and stepping down gradually. And that kind of an electric co-location basically allows us to structure this retail market. And the retail market basically has lots of different structures. And what you see on the right side is what we do with the market, and everything on the left side is comparison to other compensation methods that exist right now. And so you've got flexible loads, you've got, and they get compensated, generators at a fair retail rate, and most importantly, the customers, which is really what we are talking about in terms of incentivizing and encourage and doing something at a grid level that benefits consumers at a local level, is that you are able to reduce the electricity price by a significant amount. So at the end of the day, this is an exercise that's to say, A, you're preserving your privacy and allowing you to participate in the market, and B, at the end of the day, the final service that you're looking for is to avail of the local generation that you have from, let's say, the rooftop solars, and have it translate into something that reduces to a low electricity. So now let's talk about, with this as a framework, what is it that we can do that takes us even further? There is a significant issue when it comes to introducing smart grids, the notion of smart grids, and introducing this whole notion of differential power generation, which has a variation both in space and in time. And that is that whenever you say consumer, and we kind of draw one box and say, okay, consumer, we forget the fact that a consumer is not this monolithic entity. And so we really have not paid as much attention as we should when it comes to analyzing the impact of smart grids on low and moderate income households. So LMI is really, it means something very different in this in the context in here. So LMI households and analyzing the impact of smart grids on LMI households is a very important exercise that we should engage in. And that basically is one of the messages that I would like to get across in my talk in here. There are incredibly striking statistics when it comes to the kind of inequities that is present. I meant to get that reference for you, and unfortunately I ran out of time. The US Department of Energy basically has these numbers that there is a significant difference in between the amount of money spent on energy in various households compared to LMI. And so they spend 18% of their income, which is a significant amount. There is a whole concept, and I'm sure you have something equivalent like this in Switzerland as well, called net energy metering. So if you have a rooftop solar, essentially there is you can have a net injection actually into the grid, and you're basically paid at the retail rate for the amount of power that you inject. So that concept is called net energy metering. And so right now there is no restriction on how much you inject, and you just basically get a blanket fixed rate of compensation. Now, there is a lot of discussion right now as to whether or not this is the right thing to do. And there is a lot of studies that basically say NEM is a bad idea when it comes to impact on low-income households. Because what happens is that typically low-income household owners are often they're low-income LMI households. They are populations of color. They happen to be renters, and they are the non-participants. And because and as you have more and more increased adoption of solar PV by high-income homes, and that happens to the detriment of electricity cost for LMI homes. And one of the reasonings, and again, many of these, the models are not that simple and they're more complex, but one of the reasoning is that the way in which it comes to the business model of how utilities get compensated. So utilities get compensated based on the peak load that they serve. And in fact, bonuses of CEOs and so on are based on what exactly is the peak load. Now imagine you have a lot of solar top, that peak load basically goes down. And so in order to have the same revenue, what they do is to jack up the price. So what happens is that get unevenly distributed among the different owners. So those who don't have a rooftop solar end up paying for those who actually have rooftop solars. There, ergo, this sort of inequity and uneven distribution of the benefits of what happens with renewables. And so this is something that we really need to pay attention to, even as we go forward with all of the modeling efforts and control design efforts that we do. Okay. Do you go forward? It's not the down arrow, yeah?
Probably.
Okay, there we go. Sorry,
okay.
sorry.
No.
Okay. Okay, so this is what, unpacking it a bit more, if you participate in NEM, your electricity goes down. So if you don't, and by virtue of being an LMI, you're not a participant, then you basically obviously have to do not have the benefit. Indirectly, what happens is that invariably, whenever it comes to installing solar, there's a lot of associated overhead in terms of having internet, the ability to basically participate in a sort of a whole digital way of life and having the appropriate coordination. So that is another component. Sorry, the point that is there is that a lot of the low-income households, again, are probably not skilled to move towards a solar type of participation, say, as opposed to someone who works in a coal plant. A lot of low-income households also correspond to inefficient buildings that basically have a lot of heat losses, and so the same comments for renters as well. When there are all these different energy projects and there are all kinds of participation, like I don't know if you have a consumer choice thing with, these are the kinds of benefits that you get if you sign up for this versus whatever. And so there's lack of understanding as to what exactly are the benefits when it comes to energy projects. There's, of course, a lack of representation of, what they really are and are not able to do in the decision-making when it comes to setting up rate design and so on. And again, and this is the point that I was making earlier, that you're not able to adapt to this time of use type of rates if you don't have access to broadband, or renters with have no control over their appliances and are not getting from that. And so you're not able to afford small alliances, and all of this coupling between the net energy metering and time of use rates basically exacerbates the already limiting ability. And this is also another thing, whenever it comes to load shedding, the protocols that are used are sort of similar to the bias point that you made earlier in terms of how surveys are set up. It could be that the load shedding basically affects the same households again and again, and in which case there basically is another issue. There are many more things like this. For instance, whenever you have an outage, the kind of impact that it makes in terms of, say, for instance, all the food in the refrigerator goes bad, the recouping that loss is a much bigger effort and a much bigger part of the budget than for other people. These are all things that we really don't keep in mind. So as into some of the solutions, the kinds of things that I think we need to worry about, and there are some efforts already that are ongoing. This is just a starting point, and I think some of these have been shared with you earlier. So there are methods that basically have been looking at data-driven models to really understand what kind of disparities are there when it comes to heating costs. What are the kind of behavioral choices in an LMI households when it comes to trying to estimate energy limiting behavior? The planning process, by including an agent-based approach, you can do better. The relation between understanding how microgrids can be designed with underserved communities is something that people have started to look at. There are, of course, benefits of understanding that even if you don't have solar energy yourself, there is an overall reduction in pollution, but those things have really not been quantified yet. So some of the things that we can do, and I think these are places where we could begin the conversation. Very simple things like, is it possible to really design incentives that can help reduce the solar adoption inequalities? And I'm assuming that the next talk that talks about token system, and I like the concept of the karma. I'm looking forward to hearing about that. Probably will address more of that, but those are all things that I think we need to think about. Is there a way in which, and this is something that we don't worry about enough, can we include equity-based components in the overall cost function that we're trying to optimize? That should be a fairly low-hanging fruit, it seems to me. And we don't do enough of that, and we should. Consumer advocacy groups should be involved in the overall modeling process, and there should be coordination with technologists so that we indeed develop quantitative metrics. How much time do I have?
5 minutes.
5 minutes? Okay, all right. So I think I'm probably going to just say one, make this very brief. Okay, mobility. So this is my second example, and I think I'll skip the third example altogether. When it comes to transportation, there is always the same issue of assets and consumers. So do I have enough supply to meet with the demand? And so one of the things, so for instance, if you're looking at highway occupancy or shuttle occupancy, parking spaces, and you're looking at drivers and riders. And so it's what you really want is to make sure that you have enough assets to match consumers, right? So, but you're not always able to do that. Thank you so much. So you want, and so one of the things that really is entering the picture is that you want to do have a whole sharing economy structure so that you're able to figure out a way of using software basically to redistribute resources in order to meet with the demand. So that basically is the idea in here. There's been a lot of urban mobility components that have tried to use a transactor control strategy and use prices and fees as a way of doing resource utilization. So the main idea here is that across the board, many different cities have started to explore the use of dynamic toll pricing in order to really alleviate congestion. And the idea is simply this, that you've got basically a sensor here, and that measures the density, and then you use the density information to determine the price, and that basically changes the toll price that is here. And so the driver, you and I, basically look at the toll price and we decide, yes, we will take the dynamic toll price lane, or no, we won't. And by doing that, we change the boundary condition of that particular segment, which then changes the density of traffic, and therefore you alleviate congestion. So that's the whole idea. So we went through this exercise, and then one of the things that you have to do is to model the driver and the behavioral aspects and what exactly is the utility function, and then can we then control, can we, based on that utility function, can we then design this transactive controller? You and I are basically actuators, and by modeling the actuator, you can do a model-based control design. And then this turned out to be a nonlinear PID controller, which then we went on to design and show that it worked. You can go read the paper for more details. It worked, and we showed in simulation, and we in fact recently did a similar exercise for a highway segment near Lisbon, and there too we had a very nice example. So I'm going to sort of skip the next few slides because I just wanted to make the same point. I think I really overestimated how much I can cover in an hour, but the idea here basically is that overall, you can do a dynamic optimization problem, develop a socio-technical system model, The results are promising, and they have been actually implemented in a few places, but there are most certainly inequities that we have to worry about, and ways in which we need to address them. So clearly, the fact that you have a dynamic toll lane introduces a notion of inequity. I mean, it's like having a business class, right? So question is that the right thing to do? Are we making sure that when we design that, I mean, one of the things that we said was, okay, the highway system has a peak of $8, and normally it can go down as far as 25 cents. So if they say $8 is the peak, and they've done due diligence, and so $8 is a number that addresses this inequity issue, and so we're going to work with $8. And then we designed our control strategy. But then do we really pay attention as to where that 8 comes from, or do we have a way in which we can actually have a differential price adjustment based on some sort of a social rating system? Those are all things that we could incorporate in the design, but we don't necessarily engage in that kind of an exercise. And the only point that I'm trying to make is that some of these cross-subsidization aspects need to be addressed. And look up cross-subsidization. It's actually a very nice metric that sort of tries to evaluate, when you introduce a piece of technology, how much of an inequity does it introduce? And that's something that we should pay attention to. So the point that I'm trying to make here is that as you try to design some of these algorithms in the context of urban mobility, LMI concerns, and not linear matrix inequality, low, middle, and moderate income household, should be addressed. And one of the things that I think could be looked into are, there are bodies, entities, and organizations that basically have an understanding of what some of the incentive mechanisms should be. And some of those things can be taken into account when we design the LMI concerns, and appropriately the incentive that gets stitched together with a piece of technology. I did want to bring up a third example, but let me go into, this is just based on the issues in flight, but let me maybe mention this. This is a different example where humans and automation are working together in order to address a problem where there is a severe anomaly. It's actually a very interesting story there, but maybe I can go over that at another time. So when you imagine that there is some sort of a big anomaly, right? Lightning strikes, bird flies into the engine, whatever. There are a whole bunch of tasks that you have to do, and you have to do them in a certain timeline, right? It could be that, so let's imagine that you break down these tasks, and everything that is in orange is basically something that automation does, and everything that is in green is what humans do. So, right, so the color, that's the color legend. So immediately following the anomaly, what we showed was that you need to basically introduce some new tasks, and those new tasks are something that humans should do. And for instance, and not only that, some of the tasks that automation used to do is something that the human should take over. But then after they finish the transition, and whereas you don't touch A and B, you leave A and B within the purview of automation. Post anomaly, you then allow the make the transition and give it back to the automation, because now you've recovered and the humans have done their thing and so on. But now we did all of these assuming that humans have the best of intentions, they're informed and they're cooperative and they're not being strategic. Whereas in a compromised human, like for instance, one of the pilots has had a heart attack or not able to function, or they're being deliberately adversarial, and which what happens a few years ago in the German wings accident. So in that case, it could be very well that E and F is something that automation should take over rather than humans. And or it could be very well that if the automation is compromised as in a cyber attack, then it could be that even A and B are things probably that the humans should take over. Those are all, again, things that we need to worry about as we move towards social responsibility. So maybe with that, I'll stop. So these are the three examples. At least the first one I walked through more slowly, the other two a bit rushed. But the idea in all of these things is that in the context of smart grids, energy justice is a topic that needs to be investigated, and modeling, developing metrics and mitigation for LMI households households is something that we can do. One of the ways in which we can look at grid performance is by looking into optimization framework that includes energy justice-based metrics. And in the context of highway traffic, we need to really address the needs of all consumers. Cross-subsidization aspects can be and should be addressed. And in the flight control problem, we really need to address the fact that there could be adverse actors, either in the side of humans or in automation, and they have to be appropriately contended with. But again, I have no results to show you explicitly, but there are things that we have started to look at in the context of CPHS, but we need to advance the conversation much further to move towards socially responsible CPHS. Thank you.
I think we have time for a quick question from the audience. They're here on Zoom. Yeah.
One question about the first two examples.
Yes.
It seems like the problems you point out are very much about but I was wondering whether that's centralized optimization paradigm is the right viewpoint at all. One should rather aim for more game theoretic perspective, looking for fair equilibria.
Yeah, I mean, that's a very good point. I don't know about the conversation can start in the context of centralized, but there is no reason why it should stop there. But you might be right that it might be, you might find much better answers and much better solutions if you make that more distributed. I mean, in a way, I think you have to make it distributed as you break down the sort of the monolithic consumer representation into something that is more nuanced. So maybe as you do that, a distributed framework is probably the way to go. Absolutely. I wouldn't say at all that we should stop or start with centralized. Fair enough.
Thank you.